everyone. Thank you for being here today. Oh, I have my reading glasses on. That's cute. Thank you for being here today. I'm so excited for this conversation today. I've got Dr. Jonathan McDowell. I'm assuming he's doctor. He's a PhD in astrophysics, astronomy. We'll have to ask him to get the exact title, but I'm so excited to talk to him today about universes and everything. And he told me when we met, he told me that my questions are sort of like from here to here. And I was like, yep, that's where they are. So without any further ado, and we're on Zoom, and so there's a lag, and so I'm going to try really hard not to talk over Jonathan, so it probably will come across as me not being attentive. It'll sound like I'm not paying attention because I'm like waiting for him to finish, so I apologize in advance. But Jonathan.
Hi, Pam.
There you are. Hi, Jonathan. So nice to meet you.
That I'm on the moon and we're having a light lag.
It totally. And like, have you watched that show Away on Netflix?
I haven't seen it yet. No, I hear mixed things.
I watched it, and I shouldn't say this. I tell people it's sort of like eating a giant bag of Fritos, and afterward you're like, oh, what have I done? but they have they have instantaneous texting from Mars. The trip to Mars back home, which.
Yeah.
Yeah. So anyway, I'm so excited to have you here. Thank you. Tell us first of all, so you are a doctor of astrophysics. Tell us about just give us a little brief who you are.
Yes, I have a PhD in astrophysics. So I started off as a theorist, studying the early universe in my youth in Cambridge, the real Cambridge in England. And then I moved into more observational stuff. And studied quasars, which we can talk about. That's basically humongous black holes in distant parts of the universe. First with radio telescopes, and then more recently with X-ray telescopes. But I've worked in astronomy, for decades now, and everything from the Big Bang to nearby asteroids. And so. I'm really sort of interested in all kinds of different things in space. And then I have this other life where I have a newsletter on space travel, which is talking about satellites and spaceships and what's in orbit this week and things like that. And so really I flip back and forth between those.
That's awesome. I just got a comment. I have this program called eCam, which you and I have been talking about, and I'm like just learning it. And I just got a comment from a woman named Kay Vreeland. She says, astrophysics is so cool. This is an exciting conversation, and I totally agree. I'm so excited.
You're asking whether it's physics or astronomy, and this sort of goes back, this is like a 100-year argument, right? Because the astrophysicists were very defensive back in the 1890s. They were a new thing. And there became this sort of mantra that astrophysics is what's important. Astrophysics for me is the rules of the game. And so astrophysicists are interested not in this particular star, Kepler-32b or something like that. They're interested in how do stars work in general, right? Or how does this kind of star work? Not in whereas astronomy is more the history and geography of the universe. It's the individual objects. It's where are we? And for a long time, I think the astrophysicists have been so dominant that it's been sort of astronomy's been considered lesser. I consider myself both. I think both are important and both are fascinating and both are good science. And so you can call me astronomer. It says astrophysicist on my PhD, but I don't mind either way.
Awesome. So thank you. Yeah, your Twitter says astronomer, so I think that's what I have you listed here as. But and I know that you being a strong scientist, I might ask you some questions you don't know the exact answer to, but I just want to invite you to, you can say, I don't know, but then speculate, because I'm so curious what you think. So
I'm not afraid of speculating as long as, I make clear that that's what we're doing.
Perfect. So I wanted to start with, I think that how we met, I'm not sure if this is correct, but I think it was when Pluto, was it Voyager? What was the space shuttle thing that was going past Pluto?
Horizon.
Horizon. And I think it was during that, and we were watching on Twitter, and everyone was so excited. And I think that's how, which brings me to my question. Why did Pluto have to get demoted? Why,
Well,
Jonathan?
you say demoted, right? But I don't agree that it was demoted. I think that it was the runt of the planet litter, and now it's the king of the dwarf planets. And so actually, I think it's a promotion into a different class. And really, so what it comes down to, right, is that in astronomy, gerrymandering is frowned on. You know, you need to draw your boundaries in a way that's based on a consistent rule. And so if you define a rule that makes Pluto a planet, what that means is that there are also 200 other things that are also planets and out in the Kuiper Belt. And so do you really want the kids in school to have to learn 200 names instead of 8, right?
Yes,
So that
yes.
the choice is not 8 or 9, the choice is 8 or 200. And so there's another thing which I think gets away from this whole argument, which is that I think actually planet is not that interesting a concept anyway. That the concept, the word I tend to use is world. And the difference for me is that not just planets, but also large moons are worlds, right? So Titan, the biggest moon of Saturn, you know, it has an atmosphere, it has lakes, it has, you know, all the features that you would want on a world. And so and just to demote it from the fact that it happens to be going around Saturn instead of going around the sun doesn't seem like a sensible choice to me. And so my advocacy is that yeah, we have the 8 planets, which are the big things that travel in roughly circular orbits around the sun. But we also have about 200 or 300 worlds, which range from the planets through the dwarf planets, through the larger moons of the outer planets, and also our moon. Anything that is big enough to be round due to its own gravity, right? And if you have a stone, right? A stone can be any shape if it's small. But if it gets too big, then the ends get pulled in due to gravity because rock can flow if you push it hard enough. And that's why there are no mountains higher than Everest on the Earth, right? Is that if you had a mountain 10 times as high as Everest, it would squish down under its own weight. And so anything sufficiently big is round. And for me, the solar system is divided not into planets and moons and asteroids, but into worlds and rocks.
So, okay, this is probably a stupid question, but there are no stupid questions, right? So, when you're saying that a moon can be a world, does that mean that a moon, I mean, I'm assuming we know that in our solar system there are no inhabited moons, but could a moon be inhabited somewhere else?
Absolutely it could. And that's one of the reasons why astronomers are really enthusiastic about hunting for what we call exomoons, moons in other solar systems around other stars, because we think that that might actually be the most likely place for life elsewhere in the galaxy.
Right.
Because there's a lot of, because you have a lot of these gas giant planets, right? And a lot of them are kind of in the right distance from their stars to be sort of temperate. And moons orbiting those planets then are sort of in the right ballpark. You can get a lot of them. And also, as we've studied the moons of our solar system, we've discovered that they're much more interesting than we used to think. Not only the lakes of Titan, but a number of these worlds, like Ganymede, like Europa, like Enceladus, have interior oceans under the ice, right? And so they look, oh, it's this ice world, but in fact, a few miles down under the ice, it's ocean, it's water, and water we think is a potentially good abode for life, and there's energy there because there's tidal forces. That's another reason why moons are nice, because as you orbit the planet, there are sort of tides on it that then provide heating. And so it's a source of energy.
So our moon, like we have the dark side of the moon, right? Which doesn't get to the sun. No, you're shaking. Okay, so I'm going to ask my question, and then you're going to correct all my incorrect assumptions. So when you say that, I think, well, our moon has one side that goes toward the sun, and so if we were living on a moon, wouldn't we have all day and on one side and all night on the other side? Or how does that work if you were living on a moon?
Well, because, so let's think about our moon, right? And every 14 days, you see a full moon. It's all bright. And then 14 days later, you see a new moon where it's all dark.
Right.
And that means it's nighttime on the side facing the Earth, right? And it's daytime on the far side.
Okay.
Because what makes day or night is whether it's facing the Earth, but whether it's facing the sun.
Right.
And so, in fact, the far side has days and nights, and the near side has days and nights. And so there is no dark side of the moon in that sense, right? It's Pink Floyd just, screwed it up. So it's dark in the sense of unknown, historically, not in the sense of unilluminated.
Actually, dark.
And so actually this is why the moon is a horrible place to live, because it also gets really hot for 14 days and then really cold for 14 days, right? Because there's no atmosphere, so there's no sort of evening out of the day-night temperatures, and you've got these very long day-nights. But a moon with an atmosphere can have a more even climate, and it has it has both the light from the star and also the light reflected off the giant planet towards it, right? And so it's sort of like it's a bit Tatooine-like. It has two bright things in the sky, you're absolutely right, though, that there are problems when you get what's called these tidally locked worlds. And so our moon is tidally locked to the Earth. We see just the one side, and it's not just moons. Actually, a lot of worlds, a lot of planets around other stars are tidally locked. And Venus is almost tidally locked. It turns really slowly. But in other solar systems, we expect that a lot of planets will be tidally locked, having one face to the star and the other face out. And there, bad things can happen, because then the atmosphere gets so cold on the night side it freezes out. And then the dayside atmosphere rushes in a big wind to fill and then freezes out again. And so you end up with, instead of a nice world with an atmosphere, you end up with a barren rock facing the star and a patch of ice on the far side, which used to be the atmosphere. And so that wouldn't be very nice.
Okay, and just FYI, my sister texted in, or she wrote in, she's learning so much. I'm so excited too. So, so let's talk about what makes a planet habitable. Is it habitable or habitable? Habitable. What makes a planet habitable? Because I'm hearing atmosphere and I'm hearing not tidally locked. Tell me if those are correct, and what else makes a planet suitable for life.
Yeah. And so, it's a little premature for us to be too dogmatic about it, right? But certainly tidally locked is probably an issue. Although you might have, along the Terminator, you might have, a nice strip that was okay along the day-night boundary. You need to be in what we call the temperate zone. Used to be called the habitable zone, but that's too misleading, because there's too many uninhabitable planets in the habitable zone. It's hard to be habitable, right? And the more we find these other planets around other stars, the more we realize how lucky we are here on Earth. There's all kinds of ways that nature can kill you. So you need to be, but we do think liquid water, right? And to get liquid, you need to be at the right temperature. And so if we're just talking about a planet going around a star, then it needs to be sort of at the right distance from the star so that it's not boiled and it's not frozen. And how far that is depends on the star, right? If it's going around a red dwarf star that's really feeble, you might be really quite close in to be toasty. And if it's around a big blue supergiant star, you might have to be really far away to avoid getting fried. So that's one thing. Another thing that can go wrong is that even if you're at that right distance where you've got lots of water and stuff, you've got to have the right size planet. So if you have too big a planet, it turns into not necessarily a gas giant, but it can be what we call a mini Neptune, where there's just a big, thick atmosphere, thousands of miles thick, that wouldn't be good for life, we think. And then like totally crush anything on the surface. Although, maybe in the clouds, it's hard to see, but maybe. And then another thing that can go wrong is, if your star is, for example, if it's one of these little red dwarf stars, some of them are really active. They have mega solar flares that make ours look pathetic. And so, if you're getting irradiated by X-ray, huge X-rays and particles and things like that every couple of weeks, that might make the mutation rate too high for stable evolution, right? Or it might just give everything cancer and kill it off. So that can be good. And worse, if there's that kind of irradiation, or even just a strong solar wind, might blow the atmosphere off the planet and leave it without an atmosphere. So you don't want that. There are plenty of planets we found now which are, in fact, the conditions are such that it's molten lava on the surface. So there's some planets have different chemical makeups. So you can get a planet that is more made of carbon than silicon. And so there's a planet we found which, I'm trying to remember the name, and I don't remember it. It's 55 Cancri E.
Good name.
And it is, we think it may be made of diamond, which sounds cool.
Yes.
With graphite on the crust, but it's also going to have if it has an atmosphere, the atmosphere is cyanide, and there's all kinds of bad things about it that make it less than you might think from it having being made of diamond. So you can also have plants where if the hydrogen got removed a little earlier, there's an object called Lisa 436b that we think might have helium instead of hydrogen. And then with hydrogen, who needs hydrogen? Well, H2O is water. So if you don't have hydrogen, you don't have any water. And so that's not great. So there's all kinds of things that can go wrong. And we see it. Every time we find a new planet, we go, oh, this looks cool. And then we sort of study, oh, that's weird. What's going on here? And then go, oh, yeah, okay. That's really unpleasant. Don't want to go there.
So do we think that, or do we, by which I mean you and scientists, do we think that a planet that is habitable, would it have an atmosphere that we could breathe, or could it have a completely different something?
Right. This is the old life as we know it question, right? Is we know how to look for life as we know it, but what about life as we don't know it? Well, and it's really hard, right? We don't. And here's the problem: is that let me go back from life to just planets and solar systems. So until the 1990s, we knew of exactly one solar system, and
I was going to ask you about that. I have to go back to that, but okay, go.
Yeah. So all the theories about how solar systems formed were really good at making solar systems that look just like our solar system.
Amazing. And
the very first other solar system we found was totally different, right? It had a big Jupiter planet right near the star. And so excuse me.
It's okay.
I don't even know where that is, so I'm just going to let it that was actually an exoplanet scientist trying to reach me. So maybe to correct me.
Oh, no. That's fine.
But actually a specialist in exoplanets. I lost my train of thought. I'm so sorry.
You're talking about the first solar system that we found other than ours.
Right. So once we had two, right, totally different. Overnight, all the existing theories of how you form solar systems went out the window, right? So having two of something is way better, is much more than twice as good as having one of something, right? And so the same is going to be true about life. When we found the first extraterrestrial life, we'll have a much better idea about the scope of what life can be, right? Because right now all our theories make life that's kind of like us, because that's the only thing we know. And you know, yes, there's been speculation about silicon life and all these other kinds of things, but really it's a stretch. And so as far as we can tell, it's hard not to do it based on carbon. It's hard not to do it based on water, just because of the special properties. If you're going to have something based on chemicals, let's say, then it's probably going to be carbon and water based. That's what we think. Oh boy, could we so easily be wrong? and not just mention it. And then there's, I mean, I believe, right, that the critical sort of definition of life is one that involves sort of entropy processing and information processing. And in particular, you know, we have to distinguish, of course, between life like bacteria and life like humans and Klingons. And so, you know, if you want sentient life, right, it's all about information processing. And patterns, it's patterns. And one thing as a mathematician, I was trained as a mathematician, and one thing I believe is that patterns are fungible. In principle, that has sentient, for example.
Hello?
And so maybe there's a substrate. And then we're getting a lot of feedback here.
Yeah. Are we better now?
And, let's see how that goes. So you see what I'm saying? That you know, maybe you could have life in a nebula based on electrical patterns in, you know, in the nebula, and that considered alive. What does it mean to be considered alive? What would your test be? Suppose you find it. How do you decide whether you call that alive or not? Right? That's ultimately. I don't think nature has, you know, these definitions, right, are human definitions, and so it's a question of, is it more useful than not to consider this thing alive? In the same way, right? And so that's something that we'll have to argue out when we find it.
Well, and I think it also brings up interesting ideas of what is intelligence, and, you know, what is, because when you think about octopuses, for example, an alien coming to, I was going to say the United States, I mean Earth, an alien coming to Earth might look at an octopus and be like, that is so smart, that must be part of their sentient life, right? Like, just because we can't talk to them doesn't mean that they're not intelligent. And is there a line at which you say, okay, well, this is what qualifies as intelligent life? Is it civilization? Like, what are you looking for?
So what you're looking, I mean, what you're really leading to, right, is the Turing test, right, which is the test of, is my computer really alive, right? Which is, you talk to someone over Zoom with the video off, and you try and figure out whether they're human or not. And if they can fool you into thinking that they're human,
or a telemarketer.
Yeah, right, exactly. Then it's not useful to say that they're not human, right? And you should give them citizenship. And although there are some humans who don't pass the Turing test, so there's that. But some of them in positions of power. Anyway. So I think these are great questions to ask, and they don't have predefined answers, right? It's something that the answer is something that we as humans have to agree on. You know, in an evolving way. It's not, and so do we consider, for example, viruses alive? Right? There's been, there's different opinions about that, and there's no, it's not that there's a right or wrong answer. There's a choice we have to make in what we decide to call alive. And the trick in science is to make the choice that ends up being most useful and most constructive, right? Most productive. And so, and again, which is right back to the thing about is Pluto a planet, right? You can pick a definition in which Pluto is a planet, but is it a useful definition, or does it get you into more and more awkward corners? Right, as you go on, and that's the way we have to decide about what we're going to make words mean when we take them into new areas that we haven't been before.
So can you talk about the Drake equation and talk about what it is? And then I should have looked up at when it was formulated, because has there been an evolution of, pardon?
I think it was 1962.
Okay, so has there been an evolution in that idea? Where do you stand on Drake equation?
I mean, I think the Drake equation is a really useful talking point. It's the way that I think about it. So that for those who are not familiar, right, the Drake equation is an equation that tries to guess how many aliens are there. Right, in the galaxy. And so if you want to go, well, how many civilizations are there in the galaxy? Then you break it down into all the things that can stop you having a civilization, right? And so it is one way of thinking about it. And so it's like, the first thing is, you need a star, we think. So if we're sort of, let's assume that we are looking for biological, meat entities, right, or plant entities or something like that. But recognize what we immediately recognize as oh, that's an alien, right? So first they need to be in a star system. So how many star systems are there in the galaxy? There's 100 billion. How many of those star systems have planets? That's a number we didn't know in 1962. We've only found out in the last few years, and now we know, right? And the answer is almost all of them. And which could have, it could have been that in 1962 it was a perfectly respectable theory that our solar system was a freak and that we were the only solar system in the galaxy, right? In which case the chances of life elsewhere would be really small. And the fact that we now know that it's the opposite extreme, made the chances of life elsewhere go way up, right? And so that's the usefulness of the Drake equation, is you multiply all these factors, does the planet have an atmosphere? Does the probability that the planet makes life? Probability that life evolves to sentient life? Probability that sentient life hasn't killed itself by now? And that's the big uncertainty factor, right? Because so there's the final term in the Drake equation is average life of a sentient civilization, and the definition of a sentient civilization by Carl Sagan specified was one that has radio telescopes. Because otherwise you can't talk to them, right? As the idea, and so, but maybe that's a little narrow, but it gives you the idea. And so the best guess for the average lifetime of a civilization with radio telescopes is about 100 years. Because if you look at the one case we know, it looks like they might not last much longer. and so that makes and that's small compared to the lifetime of the galaxy. And so, therefore, there might have been huge numbers of other civilizations in the history of the galaxy, but they all killed themselves off very quickly. And so there's none around now to talk to, right? And that might be the way to bet. So it's not like you can actually use the Drake equation to get an answer, right, of how many other civilizations there are. But it's a useful tool to make you think about where the choke points are in getting a civilization, right? Which are the things we know really well? Which are the things that we could measure? and which are the things that are really uncertain. And so we've been working our way down that equation. And so now we know how many planets there are. Now we know we're on the way to knowing how many planets there are with, like, you know, reasonably good atmospheres, right? And the next step is going to be how many of those have some kind of crude life. And that is the challenge for the next generation of astronomers. And I think, you know, we may have an answer, maybe not in 20 years, but probably in 50 years.
Okay, tell me more, because that is exactly what I was going to ask you next. So I'm going to just do my little put my books up here. The reason I wrote my books, Universes Inside the Lighthouse, the Balky Point Adventures, and so on, was because I have this, like, knowledge that definitely, in my opinion, like, there's no question in my opinion, there are alien intelligent life forms out there in the universe somewhere. But I also I don't think they're here, and I don't think that I'm going to get to know them in my lifetime. But 20 years to 50 years is not, you know, I intend to live to the tricentennial, which is 2076, so that gives me time. So tell me more. Why do you think that timeline?
Well, what I'll say is this. First, I also believe that I mean, there's nothing magic about life, okay? And there's nothing magic about the Earth, and it's a big universe. So somewhere out there are other species. I'm certain of that. Right. But it's a big universe. They're not necessarily close by, right? There may not be any within this galaxy or within, you know, the Virgo supercluster of galaxies, and maybe even further than that. So that's the question: is, are they one per supercluster of galaxies or one per every 5 star systems? And that's, you know, that's a big uncertainty. And so so in just finding bacterial life is what I'm saying is sort of, or that level of life is something we can now hope to do within the next generation. And the challenge there, and so you saw maybe the new result that came out a couple of weeks ago about the detection of phosphine in the atmosphere of Venus.
Oh, yes, yes.
There's this new chemical they found that on Earth is only made biologically, right? It's made in things like penguin poop. So
they have penguins on Venus.
Yes, exactly. And so, you know, it's made non-biologically in gas giant planets, but the conditions you need to make it there are not present on Venus. On the other hand, neither are there penguins. So it's a little uncertain, right? But some people got very excited about this because it's like, okay, maybe you could have the right kind of bacteria in the atmosphere of Venus living in the clouds, which are less horrible than the surface, because anyone doesn't know Venus is like a pretty unpleasant place on the surface. You know, hundreds of degrees and sulfuric acid rain and and 90 atmospheres pressure crushing you. And so, but up in the clouds, you know, maybe. So the way we did that right is not by sending a probe to the atmosphere of Venus and tasting the atmosphere. It was by looking at the sunlight reflected off the Venus clouds. And each molecule and each atom leaves its fingerprint in the light. It absorbs certain colors. And so we can do CSI on the light to find what are in the atmosphere of Venus. And in the atmospheres of stars, and then surround up with stars, and so on. And so this magic of spectroscopy that lets us do this DNA fingerprint of the light coming from the sky lets us chemically analyze things that are hundreds of light years away, right? Which is mind-boggling in itself. And that's the tool we're trying to use to search for life elsewhere. And so there's two things. There's one, can you get the technology to the point where you can actually measure these chemicals in the atmospheres of distant exoplanets? And the other thing is, can you get biologists to agree that those chemicals can only be made by biological activity? And this is an old thing that goes back to when the Viking probes landed on Mars. They saw certain signatures, right, in their biology experiments that for a couple of weeks it was like, we found life on Mars, yay, right? And then some other chemists came in and go, well, actually you could have that by this weird chemistry. And so the history of searching for extraterrestrial life has been, oh, we found it, oh no, that signature can be done by sufficiently clever chemistry, it doesn't prove this biology. And I think that we have several more cycles of that to come. But eventually we may be able to understand what is, the term of art is a biomarker, an indication of life that, so if you see oxygen in the atmosphere of the planet, and if you see, certain other chemicals that, look like they maybe were created by life. And you know that, for example, all the oxygen in our atmosphere, right, is here as a result of life. A billion years ago, the Earth did not have oxygen in its atmosphere. That all comes from like photosynthesis and stuff.
Yeah.
So there are, so there's going to be detection of some biomarkers, and then maybe 20 years of argument between the biologists and chemists about whether it really proves anything. And that's what you...
So I saw a thing today, or yesterday, because one of the big challenges, obviously, is even if there's life out there, how do we connect with it? It's a long way away. I saw an article, or I saw a headline that I didn't read the full article because I knew I wouldn't understand it, and I thought, you can explain it to me. That there is a new theory of time travel that doesn't create a paradox. Did you see that article today?
I did not see that.
I'll send it to you. So, because obviously, it's one thing to know that they're out there, which we know, you and I know. So we're at about 200%.
Then you've got to talk to them.
Then how do we find and how do we talk to them? And do you think that a civilization's lifespan is going to be too short in most cases to get to that point where we can actually connect?
Not necessarily. I'm an optimist. I think that there must be some civilizations who don't elect idiots. If there are enough of them, one of them will figure it out, right? But here's the thing. The bigger problem is this. Suppose in science fiction, right, when you meet the aliens, their technology is usually about 100 years ahead of ours, right? And it's ahead because that makes narrative danger, but it's not so far ahead that we can't beat them by uploading a Microsoft virus to their computers or something, right? And so but that's not what it's like, because here's the thing, right? What's the probability that the aliens are within 100 years of us? That's like, if you think about the lifetime of how long it's been since the galaxy had enough heavy elements in it to support the evolution of life and things like that. That's billions of years. And so to meet an alien that's only within a few hundred years of you, in terms of age, if you have civilization age, that's like the next person you meet, if you were to ignore COVID and walk out of your house and meet someone on the street, right, is the next person you meet was not only born the same year as you, but on the same afternoon as you. Right? It's like really unlikely.
Okay.
And so, mostly you meet someone who's like, you wouldn't be surprised to meet someone a few years different in age from you, is the first thing, right? And in this context, that would be 100 million years behind you or 100 million years ahead of you, right? So either they're like dinosaurs or they're gods, right? And if they're dinosaurs, they don't have space travel, we think. And well, science fiction stories about that, but you know what I mean. So maybe like lemurs or something, right? So if they're behind, they don't have space travel. If they're ahead, we are as ants to them. And so, is there anything that we have in common to talk about. And so I think that's the real challenge with aliens is that probably they are at such a different stage of evolution that it's kind of a relationship mismatch.
So is that almost like saying that they wouldn't consider us intelligent life because we're so far?
Yeah. Or, you know, one of the resolutions of the Fermi paradox, right, is that they know we're here, but they're like, they've put like do not disturb signs around us because they don't want to tread on us, right? The shock would be too great. And so, yeah, so I think the chances of finding a species which is what we kind of look for like friends, you know, like buddies that we can hang out with and Zoom with, seems low just because of the timescales in the galaxy. Now, that may not be right, of course, because it may be that evolution doesn't work like that, and that, you know, there's a ceiling to the sophistication that civilizations can get, and really we like to think we're the summit of evolution, right? And so it's natural for us to imagine that, yeah, aliens couldn't be that much ahead of us, right? And so one suspects that is a failure of a limitation of our own brains. But maybe not. Maybe it's true. Maybe it's sort of like the Turing machine thing that there's a universal computing architecture, and whatever hardware it runs on, you know, it's basically pretty similar, and intelligence is intelligent. So that would be a counter theory that would open the way to the Star Trek universe with all of these somewhat comparable species interacting, and a nice united federation of planets, and you know what we all like to end up with. So I can't rule it out, but it's not like, you know, a priori it doesn't seem like the most likely outcome.
Okay, so time is flying. I'm having so much fun. I want to talk about universes. I want to talk about parallel universes, and I also want to talk about mirror universes, because I wrote into one of my books a mirror universe, and I just was like, I'm just going to make it all up. So I'm curious about how you speculate, I mean, unless you know for sure, but how you speculate a mirror universe would operate in terms of time. I'm just going to tell you everything I want to know, and then you just go. What's the evidence for parallel universes or alternate universes? Where are they? And anything you want to say about time? Is time multidimensional or two-dimensional or one-dimensional? Go.
All right, yeah. The first thing about parallel universes, we just don't know. So there's this word multiverse, and I'm starting to hate it because it's been used to mean like at least 5 totally different things. And so what do you mean first by universe, right? So let's say you and I live in an ostensibly 4-dimensional space-time. If you believe the string theorist, there's another 7 dimensions that are so tiny that you don't notice them because they wrap around on themselves in like half an inch, right? So if you move in that direction, you're back where you started immediately. But let's ignore those and say we've got 4 dimensions, 3 of space and 1 of time. And that universe is contiguous in the sense that, you know, it's one big expanse. But there's only part of it that we can see. Because if you think of, and what we think is like this universe is full of galaxies, right? And we're in one of those galaxies. And if you go a really, really, really long way away, you still get galaxies. Because sufficiently far away, the light from those galaxies has not had time to reach us yet since the Big Bang. And worse than that, because of dark energy, which is a relatively recent discovery, the expansion of the universe is accelerating to the extent that those galaxies will never, the light in those galaxies will never reach us because the universe is expanding too much. And so we will never be able to know about those parts of the universe. And so in that sense, you can think of them as separate universes. However, there is no boundary, right? There's a galaxy halfway between that sees both ways, right? So so we think that the laws of physics, and here's one of the most profound and fundamental things that I've learned in studying astronomy, which is this. So, I talked about spectroscopy and how you can detect chemicals from doing CSI on the light. So if you look at a galaxy that is 4 billion light years away, and we're seeing it as it was 4 billion years ago, because that's how long it took the light to get there, and you look at its spectrum, you see patterns, so you make a rainbow from its light. You see patterns of missing colors in that rainbow that are the chemical fingerprints of atoms like sodium. And so, and not only light, you can see the fingerprint of sodium, for example, or calcium. Right? That's one that's very commonly we see. And those are very recognizable patterns in the light. And so it's unambiguous. That is sodium. And what it says is, not just we can figure out what these galaxies are made of, but that they are made of the same things as us. And if you take a sodium atom and shake it, the light that comes out of it comes out in the same wavelength patterns that it does in the lab here and now, or 4 billion light years away, 4 billion years ago. So the laws of physics are the same every when and everywhere. And that we didn't have to be true, right? And so what we think is that's going to be true even, in the bits of the universe we can't see. That there's every indication is that the laws of physics are the same everywhere, that the periodic table is the same everywhere, that all of that stuff. And so, which is good, it means physics is an actual subject that's worth doing, and chemistry and all those other things, right? It's not just some local fiat that might change next year. So that's our universe, right? Which works in a certain set of, Planck's constants the same everywhere, things like that. So the question is, so I don't think it's useful to think of that as a multiverse, because even though there are bits we can't get to that we don't share history with, there's still a contiguity. Another issue is, so before the Big Bang, does it mean to talk about before the Big Bang? And so time, we think, is sort of a variable that, if you like, space, as you get close to the Big Bang, space and time kind of melt into some quantum stuff. And it doesn't make sense then to use the words before to extend that to the beginning of the Big Bang. And so it could be that our universe is a quantum blip that formed from another universe with a completely independent time coordinate, right? That isn't before or after, but just different, right? And so there could be other universes in that sense, where there is no physical line that you can draw from here to there, even going through time. But there's also no way to get there from here. There's no way to contact them. They're in our infinite past, in a sense. So there's another idea, which is in quantum mechanics, you have the many worlds hypothesis, which is that, when Schrodinger's cat, right, we do the Schrodinger's cat experiment, and the cat's either alive or dead, in fact, the universe splits in two, and there's a universe in which it's alive and a universe in which it's dead.
Right.
And every time, a quantum transition happens, it splits the universe one more time. And so there's like gazillions of universes being created every second. And which seems wasteful and implausible, but, not ours to say what nature should do. But I'm skeptical of that interpretation as a real interpretation. But maybe there's some subtlety which makes the separation, the splitting, be more discrete than that. Only have it, and so instead of having infinite numbers of infinitesimally subtly different universes, you have like a more finite number of, concretely different universes, and then you get into like the sliders kind of game of can you get from that slice to this slice and be in the universe where the Nazis won World War II, or hang on, looks like we are in that universe now, but anyway, you know what I mean. So you have I mean, I doubt that, but and that discreteness is something that we don't have any suggestion of in physics at the moment. But there are, the fact that this many worlds kind of thing leads one to think in terms of this. What would it mean to have these universes, and what's the axis along which they are separated? You could also have universes in a higher dimension. So suppose our four-dimensional world sits in a 10-dimensional world.
Oh my.
Let's make it a 5-dimensional world, right? And so you have, our world, and then there's another 1 inch to the right. There's another 4-dimensional world. 1 inch to the right. There's another 4-dimensional world. And so the question is, how do you propagate in that direction, right? Is there any connection is there any interaction? Is there any physics that lets those two, the adjacent layers, talk to each other? If there isn't, then it's hard to really understand whether it is meaningful to think of them as existing. And if there is, then you'd expect there to be physics experiments that you could do to detect their effect, and we'd probably at this stage have found in accelerators evidence of these extra dimensions in some way, right? And so, I'm a bit skeptical for that reason, that I think we probably know about them by this stage, but keep it open. So yes, there are. I think, so as a science fiction writer, I think it's legitimate to play with these parallel universes to a certain extent, but it's certainly not something that, it's more that we don't have strong evidence against them than we have any reason to think that they're there.
It's possible.
But you can't quite rule it out, so go for it.
Yeah.
So far.
But talk to me a little more about, excuse me, about time. And, because is time, I mean, when you think about the fact that when you're seeing light from 4 billion light years away, that you're seeing 4 billion light years in the past, whatever, in that sense, time is not, I mean, you'll know the word I'm looking for, but it's not it's a relative thing, I would say. Is that accurate? Well,
that aspect, right, is nothing fancy. That's just the fact that I'm seeing you as you were 2 seconds ago, right, because of zoom lag, right? And, we normally ignore that because you haven't changed much in 2 seconds, right? And so, when you're in I hear when people go to these things called sports stadiums that they can hear the delayed, sound travel echoes, right? That they hear what was being said a couple seconds ago because of the finite speed of sound across there. That's the same effect is the effect that, when Wolf Blitzer on CNN talks to Christiane Amanpour in Iraq or something, right? She sits there looking frozen for a minute and then goes, "Hi, Wolf," right? Because it's speed of light. You're seeing her as she was a few seconds ago, and she's seeing Wolf as he was a few seconds before there, right? And so that's exactly the same thing for these galaxies, right? It's just that they're so far away that the lag is so long, so having a conversation would be really tedious because it takes 4 billion years to get the reply. And so there's nothing magic about that. That's every day. And I say that to emphasize that because there are really weird things about time that do happen. And so and I kind of, washed over them a little bit. Time and space are, famously are relative, right? As Einstein told us. What does that mean? Well, I think the most important thing to understand is, the way I think of it is this. If you think that you're not moving right now, you think that you're sitting at home with the speed of 0.
Right.
But that's actually not true. You are traveling at the speed of light.
Right.
But you're traveling at the speed of light towards tomorrow. Because tomorrow is a direction.
Tomorrow is a direction.
and so here's the weird thing about time, is that you're always traveling at exactly the speed of light. So now, if you start moving in space, like say you get on an airplane, and now you're traveling at 500 miles an hour in space, you're traveling slightly less fast in time, because your total speed, in a special relativity vector sense, has to add up to the speed of light.
Okay.
And what that means is that when you arrive at your destination, because you're traveling at that speed, you're actually slightly younger than you otherwise would be, by like a nanosecond, right? I think like it's some tiny amount, but big enough.
Skin, it looks good.
Yeah, exactly. But, you know, we've actually measured that. We put atomic clocks on planes and flew them around the world in opposite directions and compared with the clock that stayed at home. And it agreed exactly with the predictions that this effect is real. They experienced less time. And if you think of time as tomorrow as direction, right? Tomorrow is also like a place that you're going to, right? And you're going to in the future at the rate of 1 day per day, and you're not moving, right? And so, in a sense, what's happening when you move in space is that you're taking a shortcut to tomorrow, so it doesn't take as much time to get there, right? And so this idea that the time we experience is just a projection of this four-dimensional speed that we have. And here's the fun thing about it, right? So suppose you go faster and faster and faster, then as you approach the speed of light, the rate at which time passes for you is slower and slower and slower. But then the most you can do is put all of your speed in the space direction, right? And then you're traveling with the speed of light and not traveling in time at all. But you can't put more than all of your speed in this. So this is why you can't go faster than light. It's not that there's some barrier. It's that you're always going at exactly the speed of light, and it's just a question of whether you're going in the tomorrow direction or in the space direction,
Okay.
right? But you can't put more than 100% of it in any direction.
Okay.
And that is why the speed of light is fundamental. It's actually just the speed of speed, or the things that have no mass, like photons, like light beams, travel always maximally in the space direction, so at the speed of light, and not at all in time. So it's the same time at every point along a beam of light. And that's, don't even try. Whereas the things with mass, like me, I can't put all of my speed in that direction. I can only put some fraction of it. So I can never quite get to the speed of light. But nothing can go faster because everything is going maximally at that speed in one direction or another. So that's the four-dimensional way of thinking about why space and time are mixed. And so what it means is, there's another effect, which is that gravity affects time. And so if you are sitting at the bottom of a gravity well, like on the surface of the Earth, time is running more slowly for you than an ordinary person out in space far from gravity, right? Far from planets and stars and stuff. And so, so clocks run at different rates depending on the local gravity, and that's another aspect of Einstein's theories. And so the effect of that, you have an atomic clock on a satellite 15,000 miles up. It is going to run at a different rate than the same atomic clock on the Earth. And if you are relying on that atomic clock to tell you how to get home, because it's your GPS signal, you actually have to adjust the atomic clock on the satellite to run at slightly the wrong rate to compensate from the difference in which time runs 15,000 miles up and on the Earth. And they do that. And so that is an engineering application of the relativity weirdness of time. And so that's how, that's how this is. Relativity is not like some weird sort of, yeah, maybe I believe it, maybe I don't. No. If it ain't true, your GPS doesn't work. And you don't account for it, your GPS doesn't work. And so in that sense, yeah, time is this very fungible thing. It's very it's not fundamental in the way that we imagine it is, right? It's an emergent thing.
Well, speaking,
Carroll writes a lot of interesting stuff about time.
Is that one of the books you sent me?
Yeah, no, it's not, but I should have done. Let me just see if I can remember.
You sent me two books: "The End of Everything" by Katie Mack, and "The Planet Factory: Exoplanets and the Search for a Second Earth."
Yeah, so that's right. So I was going to recommend, all the discussions we were having about all the horrible ways in which planets can be not habitable. I lent a lot on Elizabeth's book, Elizabeth Tasker, who's an exoplanet theorist at the University of, actually the Japanese Space Agency now. And she is another English expatriate like me. And her book is called The Planet Factory.
Got it.
And it's really excellent. It's really up to date and got lots of stuff that is will give you a sense of where that whole field is right now, and a lot of the questions that you asked are addressed in it. And then for the multiverses and parallel stuff and so on, it's not quite on topic, but it dabbles with it, and again, really up-to-date view of cosmology. My colleague Katie Mack at the University of North Carolina, that's M-A-C-K, has written this book called, is it The End of Everything,
yep.
I think?
The End of Everything, Astrophysically Speaking.
Yes. They forced it to add the Astrophysically Speaking, I think, because otherwise people would think it was a politics book. But yeah, it's about all the different ways the universe might come to an end. So it's a really kind of depressing topic, but it's really entertainingly written. So if you want to learn about the current thinking about the universe in the big scale, it's what I recommend. And then this book about the nature of time is called From Eternity to Here, The Quest for the Ultimate Theory of Time, and it's written by Sean Carroll, Seancarroll at Caltech. And Sean's an old friend. He was a graduate student here at Harvard back in the day, long ago now. And he's just a really engaging thinker about on the boundaries of philosophy and physics, and so his stuff is good fun. And so those are like examples. Another thing, if you want to go deeper into the universes stuff, is one of my old bosses, Martin Rees, who is Her Majesty's Astronomer Royal, and he did well. And he's written a whole bunch of popular books, including one called Just Six Numbers, which is getting on now, but it's about how there are a few fundamental constants that describe all of the universe, and I'm just trying to see what his more recent book is called. He's written one called Before the Beginning. He's now sort of switched to writing stuff more about the future of humanity and how we're all screwing up, and what we should do. So, but he has quite a wide range, and but he's a deep thinker on the nature of the universe, and he was. If you've seen the movie about Stephen Hawking,
I need to see that still. Yeah, with Eddie Redmayne. The character that's his
kind of dorm mate friend is partly based on Martin.
Oh, how fun!
Martin's Martin's done a lot of profound work in cosmology. So I think those are some. If you want to kind of go deeper, those are all great books to explore.
Okay, well, I want to leave you with the chance to answer a question that I tossed at you earlier to give you some time to think about, and I'll preface it for our audience here that when years and years ago, back I was probably in my 20s maybe, I was thinking one day about the fact that my grandparents, previous generations would never have imagined that people would end up on the moon, like people would land on the moon. And I was curious, like, what do I think will never happen so that I can say it didn't happen or that it did happen? And I, at that time, decided my answer was, we'll never, ever, ever have people on Mars. And now here we are, and it literally could happen in the next, I don't know how many years. So I'm wrong. Now I have to come up with a new thing. What do you think? And we won't be able to guess to know that you're right or wrong until 50 years from now. So you can say whatever you want. But what do you think will never happen in your lifetime?
Right. So there's what will never happen ever and what will never happen in my lifetime.
Right.
And I think, for me, the things that will never happen ever are the things that break fundamental laws of physics.
Okay.
And we, there are bits of physics that are on the frontier that are still, we're not fully confident of, but there are areas of physics which we're pretty darn confident of. And so one of them, as I explained, is the speed of light. So sadly for science fiction authors, I believe that we will never have FTL, faster than light travel. That will never happen. And similarly, we'll and we'll never have time travel into the past.
What? No.
Right? So we'll have time travel into the future because that's what we're doing every day. Right? And as I explained with that, you can change the rate at which you go into the future by changing your speed. But the past, we will never get to. So those are things I think we'll never have. And I think slightly, let's see, in our lifetime, or in my lifetime at least, I will never have immortality.
Okay, interesting.
Well, see, for one thing, we can't break the second law of thermodynamics, which says that basically everything falls apart if you give it long enough. Okay. And so I think we'll never have true immortality. We might have, million-year lifetimes someday, but not yet. I think, for example, one way that you could imagine humans having quasi-immortality is uploading, right, into a computer, right, and then digital entities. You can imagine digital intelligences having very long lifetimes and just getting copied from medium to medium. But I think that's a lot harder problem than some writers think, and it's going to be centuries or millennia rather than decades before we can do that. Sadly, because I really want to do
Is that what you want? That's your dream?
Well, rather than die. I also don't think that we will meet aliens, sentient aliens, in our lifetime. But that's one that I could be wrong about, right? There's nothing in physics that says it won't be tomorrow.
That's
right?
true.
The big Independence Day, city-sized spaceships could appear over our cities tomorrow and we'd be toast.
They're going to be friendly. They're going to come with a mission of kindness.
Yeah, well, they're going to be like us, though, right? They're going to come with a mission of kindness and accidentally tread on us. Oops. Oh, well, I guess that wasn't so good of us, was it? So I think that, let's see, what else will not happen? Along the same lines, strong AI, sentient machines, and by strong AI, I mean, again, a computer that you would give citizenship to, right? That I think is possible in principle, but again is at least a century off, if not more.
Okay. We'll check back. I'll check back with you in a century.
Yeah, sounds good. If we get uploading done in time for me not to die. Yeah.
Jonathan, this has been so much fun. Maybe we'll have to do it again sometime. But I am so grateful to you for your wisdom and your time. And I'm a little over time, so I appreciate your sticking with us. And I know everyone's so grateful. So thank you. It's been so fun. And I wish you the best. And I'll check back with you before 100 years from now, but also in 100 years.
I look forward to talking with you again.
All right. Thank you. And let me just put I'm going to put your information up. Here's where you can find Jonathan online. And thank you to everyone for coming along for the ride today. All right.